I'm happy to introduce the Quantra system to the audience with a focus on the technology behind the viscoelastic measurement, referred to as sonorheometry, and I will also explain the various assay parameters derived by using this technology. The Quantra system is a small tabletop device which has really been designed for use at the point of care, and importantly, the system allows the direct measurement of the physical properties of the whole blood sample, referred to as the shear modulus, and is doing that by applying ultrasound technology, referred to as sonorheometry, which is a proprietary patented technology of the company. How does it work? What is shear modulus? What do we mean by that? That's explained in the next slide. Shear modulus is a measure of the stiffness of the clot, or the clot strength, and it reflects the resistance to deformation from stress parallel to its surface. And it's defined, physically it's defined as shear stress divided by shear strain, and is expressed in units of Newton per square meters, also referred to as Pascal. So it's like a pressure measurement. So at a given force applied to a blood sample in this case, or to any material, the material may change its position, may be deformed, may be displaced, and the stiffer the material, the smaller the displacement. What is important to realize is that this shear modulus, the viscoelastic properties of blood, are expressed as shear modulus, or in Newton per square meter, is not linear with the amplitude as measured by other viscoelastic devices like Rotem and TAG. And that is very important to measure the platelet contribution to the developing clot, as will be explained by the next speaker. So how does it work on the system? So we start with introducing a large ultrasound pulse into the blood, into a whole blood sample, and this is causing a shear wave and is leading to displacement of the red blood cells. At the same time, the clotting reaction is initiated because the blood comes into contact with certain reagents, so the clot starts to develop. And because of the developing of the clot, the viscoelasticity of the blood will change over time, and this will result in a change in the displacement of the red cells. And that's continuously monitored by tracking pulses. And from this echoes of the tracking pulses, the displacement of the red blood cells can be assessed, and this can then be transferred into a shear modulus. So in the end, you get this curve, which shows the change in the shear modulus over time. And from this curve, three important parameters can be extracted: the clot time, the clot stiffness, and also the clot stability to lysis. And I will explain these parameters in more detail in the coming slide. So if you look at clot time, that is done on the system by introducing kaolin, which activates the intrinsic clotting pathway, and then at a certain time point, you see the change, the start of the change in the shear modulus, in the viscoelastic properties. So that it's the time point at which the shear modulus crosses a certain threshold. This is done in the absence of heparinase, but can also be done in the presence of heparinase, and also the ratio between the two clot times can be expressed. So by comparing the clot time in the presence and absence of heparinase, it is possible to distinguish factor deficiency from the presence of heparin. If you look at clot stiffness, that is done by activation with tromboplastin, which activates the extrinsic pathway. Again, you get a similar curve. And then clot stiffness is read from this curve 7 minutes after the clot time. So there's no need to wait until the maximum clot stiffness has been reached. What you can measure at 7 minutes correlates highly with the maximum clot stiffness, and this allows to have a very rapid assessment of the clot stiffness. Clot stiffness is determined in presence and absence of a platelet inhibitor. So if you measure clot stiffness in presence of the platelet inhibitor Tiximax, it is a reflection of the fibrinogen contribution to clot stiffness. And then the platelet contribution to clot stiffness is simply calculated by subtracting the FCS amount, fibrinogen contribution, from the total clot stiffness. Then how is fibrinolysis assessed, so the clot stability to lysis? Then we need to extend the measurement time, because it is important to reach the maximum clot stiffness. And then the decline in clot stiffness is monitored for 50 minutes after reaching this maximum. And that's done in the presence or absence of the fibrinolytic inhibitor tranexamic acid. So if there is no fibrinolysis, the curves are parallel. There could be a decline in clot stiffness, but there is no difference in the decline between the curves in the presence or absence of tranexamic acid. And if you see a small decline, it will then be related to clot contraction and not fibrinolysis. In the bottom picture, you see a clear example of the presence of fibrinolysis, where the curve is really more rapidly declining in the absence of tranexamic acid compared to the presence of tranexamic acid. And comparing these two slopes then allows to calculate the CSL value expressed in percentage. And if the CSL, the clot stability to lysis, is less than 93%, which is the lower limit of normal reference range, then that's an indication of the presence of hyperfibrinolysis. So all these tests and reactions are done in closed containers, in cartridges. 2 cartridges are available: the QPlus cartridge with 6 output parameters and the QStat cartridge with 5 parameters, which includes the fibrinolytic assessment. The cartridge contains a place to load the blood sample. Blood is drawn into the cartridge, is preheated, and then mixed with the reagents, and finally transferred to the measurement chambers for the continuous ultrasound measurement. It's a very simple operation. In less than 60 minutes, the whole system is up and running. You start to introduce the cartridge, then you introduce the sample, and you press start. But this is a picture shows the layout of the QPlus cartridge. So we have 4 measurement channels. Channel 1 and Channel 2 contains the kaolin activator, which activates the intrinsic pathway, and Channel 2 in the presence of heparinase, which neutralizes heparin. Channel 3 and 4 contains a tomoplastin reagent to activate the extrinsic pathway, in which Channel 4 also contains the platelet inhibitor. And this is how the results are displayed on the system by means of simple to read dials. So on the top line, you see the clot time parameter, CTH, presence of heparinase, CT without heparinase, and the ratio. So in this example, CT is prolonged, but CTH is normal. So this is an indication of presence of heparin. And in the bottom line, you see the clot stiffness parameters: total clot stiffness, the fibrinogen contribution to clot stiffness, and the platelet contribution to clot stiffness, which is calculated. So there is a numerical value which is displayed, but also the arrow points to the place on the measurement range, and the green bar is an indication of the normal reference range. This picture shows you the layout of the QStat cartridge, which allows to measure fibrinolysis. Again, the first channel contains kaolin to measure the clotting time. All the other channels contain tomoplastin to activate the extrinsic pathway, in which channel 2 contains the fibrinolysis inhibitor, and channel 4 contains the heparin neutralizer. So in the end, you get these results expressed. So the clotting time, the CSL parameter, the clot stability to lysis, which is calculated by comparing the decline in clot stiffness in channel 2 and channel 3. And then on the bottom, you see all the clot stiffness parameters that you also see in the QPlus cartridge: total clot stiffness, fibrinogen contribution to clot stiffness, and platelet contribution to clot stiffness. So in summary, the Quantra hemostasis system is really designed for ease of use at the point of care. And sonorheometry is a unique system based on ultrasound measurement that allows a direct estimate of the shear modulus. And by using these 2 cartridges, you get a total assessment of hemostasis in terms of clot time, clot stiffness, and clot stability to lysis. Okay, I'll stop here and thank you for your attention.